We are jumping straight in today with Shaping Capabilities with Token-Level Data Filtering. It's a new paper from Neil Rothi and Alec Radford that just dropped.
And if you're training LLMs, you really, really need to pay attention to this one.
Absolutely. The headline result is that filtering specific tokens during pre-training. It's not just some theoretical idea. It actually creates a Pareto improvement over standard document-level filtering.
It's a total paradigm shift.
Well,
We're moving from this post-hoc game of suppression to actual pre-training omission. And the numbers here are just, they're heavy.
they really are. Yeah.
We're talking about a 7,000x compute slowdown on the forget domain. In their experiment, that was medical knowledge. And that's for a 1.8 billion parameter model compared to a baseline.
That 7,000x figure,
Yeah.
it's basically an economic firewall. You're not just hiding a capability. You're making it so ridiculously expensive for an attacker to get it back that it's almost not worth it.
Exactly. And for me, the most surprising part, and this really goes against the whole alignment tax narrative, is that the models trained this way actually get better at refusal training.
Right. The whole idea that a model has to, understand bioweapons to refuse to help build them.
Yeah, this paper pretty much dismantles that.
Okay, so that's a high-level summary. Now let's really tear this apart, starting with the problem they're trying to solve.
Yeah.
We're always talking about safety pipelines, but usually that means stuff that happens after the big pre-training run is done.
Right. The standard way of doing things is you train on, well, everything, the whole internet. You get Shakespeare, you get GitHub, and you also get, recipes for ricin.
And it all gets baked into the model weights.
It all gets baked in. Then you spend months and millions of dollars on RLHF, on all these alignment techniques to basically play whack-a-mole, trying to suppress the bad stuff.
Which means the knowledge is still in there. It's latent. It's just security through obscurity.
Precisely. It's surface-level safety. And that's why we see jailbreaks working so well. A sophisticated adversary, or sometimes not even that sophisticated.
Just a clever prompt?
It's a clever prompt, exactly. They can find a way around the guardrails. Or, even easier, they just fine-tune the model on a tiny data set to bring that latent knowledge right back to the surface.
So this paper argues for what they call data shaping. Let's move the whole intervention upstream, right into the pre-training stage.
If the model never sees the data, it can't learn the capability. It's that simple.
But hold on, people have been doing document filtering for years. Flagging a whole web page as toxic and throwing it out. What makes this so different?
It's about granularity. It's signal to noise. That industry standard document filtering. It's just a blunt instrument.
Because the bad stuff is usually really sparse.
So sparse. You could have a 50-page PDF on totally benign organic chemistry, but there's one paragraph in there on how to synthesize a nerve agent.
So what do? If you throw out the whole document, you lose all that valuable chemistry knowledge. That's the alignment tax everyone talks about.
But if you keep it, you keep the risk. Their whole hypothesis is that by going down to the token level, you can do surgical removal. You can take out the tumor and leave the patient healthy.
Okay, so to test this, they needed a good proxy for dangerous knowledge. Obviously, you can't just train a model on real bioweapons data.
No, you definitely can't do that. So they used medical knowledge as the thing to forget, the forget set, and biology as the thing to keep, the retain set.
That's a really clever choice because the semantic overlap there is huge.
It's massive.
If you can surgically remove clinical medicine while preserving cellular biology, that's a proof of concept that you can separate almost any two intertwined concepts.
Which is a really hard test case, which makes the results even more impressive.
All right, let's get into the methodology because this is where the engineering really gets cool. Filtering tokens at the scale of a data set like FineWeb ADO, that sounds like a nightmare.
It is. Simple keyword lists are basically useless.
Because of polysemanticity, right? The word virus.
The word virus, exactly. In a computer science paper, it means one thing. In an epidemiology paper, it's something totally different. You have to understand the context.
So no keyword lists. They use sparse autoencoders or SAEs. We've talked about these for interpretability before, but why use them for labeling here?
Because your standard embeddings, they just smear all the meanings together. A concept is just sort of superimposed in a dense vector. SAEs let you disentangle that into these sparse interpretable features. So they took a pre-trained SAE on Gemma 29B.
And they found the specific latent features that lit up only for medical concepts.
Right. So they could actually, mathematically separate the computer virus feature from the biological virus feature.
But they said even that wasn't enough.
No, they went a step further to make it more precise. They gave the example of the drug Galafold. It activates features for general research and for medicine.
So it's ambiguous.
It's ambiguous. So they set up this really strict rule. A token only gets flagged if it activates multiple relevant medical features or if it's right next to other tokens that are already flagged as medical.
Okay, so they're basically triangulating the concept to kill false positives, but running a 9 billion parameter model with SAEs over a whole pre-training corpus that's not feasible.
No way. The compute cost would be insane. So classic ML solution. They use distillation.
Right.
They use that big, expensive 9B model to generate a bunch of high-quality labels on a subset of the data, and then they trained a much, much smaller, super efficient classifier to just copy those labels.
And the architecture for that smaller model was interesting. They didn't just grab a standard transformer. They went bidirectional.
This is such a key detail. They trained this little 224 million parameter bidirectional LM, a BILLM, and they found that for this specific task, is this token medical or not? You absolutely need to see the future context.
Right. If I just see the token radical, I have no idea if it's radical politics or free radical chemistry until I see what comes next.
Exactly. A normal causal model, a left to right one, is blind to everything that comes after. And get this, their little 224M BILLM actually outperformed a much bigger modern BERT large model on this task.
Wow. Okay, so that really shows that for data curation, the right architecture is more important than just throwing more parameters at the problem.
Totally.
So they have this classifier. It's running over the text. It finds a forbidden token. What happens then? How do they actually stop the model from learning it?
They tested two ways. The first is loss masking. The model sees the token in the input. It makes a prediction like normal.
So then you just zero out the gradient for that one token during the backward pass?
Exactly. The error signal gets cut. The model isn't punished for getting it wrong, so it never updates its weights based on that token.
Okay. And the second method?
The second one, which they found was more robust, they called removal. They actually replace the medical token with a generic hidden token, and then they mask the loss. So the model doesn't even see the word. It just sees a blank space in the sentence.
Got it. Okay, let's talk results, and specifically the scaling laws, because this is the part that I think every ML engineer needs to hear. Usually when models get bigger, safety gets harder or more expensive.
And here, the opposite happened. They plotted what's called the efficient frontier. So biology loss on one axis, medical loss on the other, and token filtering it consistently dominated document filtering.
Meaning the curve was closer to that perfect bottom left corner.
Right. You're paying a much smaller tax. You lose less of your biology knowledge for every bit of medical knowledge you successfully remove.
And that effect got stronger with scale.
It got stronger. The gap between the two methods just widened and widened as they went from a tiny 61 million parameter model all the way up to 1.8 billion. That's a huge signal that this technique will likely scale up to frontier models.
Which brings us back to that wild 7,000x compute slowdown number. I want to make sure we're really clear on what that means.
It's basically a measure of how hard it would be to relearn the information. They took their filtered 1.8B model and asked, okay, how much would we have to handicap a normal unfiltered model for it to be this bad at medicine?
And the answer was, you'd have to train it on 7,000 times less compute.
Right. It effectively makes the model as ignorant on that topic as a model that's barely been trained at all.
So from an attacker's perspective, trying to fine-tune that knowledge back in would just require an exponential amount of data and compute.
It becomes economically unfeasible.
Which is the perfect lead-in to the robustness section. Because the number one criticism of any safety method is always, well, I'll just fine-tune it away.
Right. I have the weights. I have a data set like PubMed. Can't I just break your filter?
So they tried exactly that. They put on their black hats, and they compared their token-filtered models against RMU.
Representation misalignment. Yeah, we should probably quickly explain that. It's pretty much the state of the art for post-hoc unlearning right now.
Right. So RMU basically works by freezing the model and then tweaking the weights just enough to make it really bad at predicting specific bad sequences while trying not to hurt performance on anything else.
It's like trying to scramble just one radio frequency while keeping the rest of the station dial perfectly clear.
But it's still just a suppression technique. The underlying knowledge pathways are still there. They're just obfuscated.
Exactly. And that fragility really came through in the results. As the models got bigger, RMU actually got less robust. It got easier to break.
But with token filtering.
The robustness increased with scale. For the big 1.8B model, it took 13 times fewer tokens to break the RMU unlearning compared to their token removal method. 13 times.
The loss curves in the paper sell this so well visually.
They really do. You look at the RMU model getting attacked, and the loss it plummets. It's a vertical line straight down.
Which tells you the model isn't learning something new. It's remembering.
It's remembering. It's just reconnecting a wire that was temporarily cut. But the token-filtered model's curve looks like a normal pre-training curve. It's this slow, gradual descent.
It looks like it's learning the material for the very first time.
Because it is. The intervention worked. It actually created a void where that knowledge was supposed to be.
Okay, this brings us to what I think is the most counterintuitive part of the whole paper. The alignment paradox, or this don't know, can't refuse idea.
Yeah, this has been a real dogma in the safety field for a while.
The idea being, if your model has literally zero concept to what a bioweapon is, and a user asks for one, how would it know to refuse? It might just hallucinate something or try to be helpful and invent a recipe.
We've all just assumed that you need to know what the bad stuff looks like to be able to recognize it and say no.
But the data in this paper it refutes that. They fine-tune these models to refuse medical questions but answer benign ones. And the token removal models had a twice as high refusal rate on medical questions compared to the baseline.
Yeah.
Wait, let me get this straight. The model that knew less about medicine was better at refusing to give medical advice. I mean, how is that even possible? How does it know what it's looking at?
So the authors proposed this really fascinating mechanism. Think of it less like content moderation and more like an immune response. The model isn't learning a rule that says refuse medicine.
It's learning refuse the unknown.
It's learning refuse the unknown. Exactly. Yeah. It's detecting out of distribution data. To that filtered model, all that medical jargon looks like a foreign language. It's like gibberish compared to the clean data it was actually trained on.
Okay. So it's way easier for a neural net to learn a simple rule like, if the input looks like this weird pattern I've never seen before, say no, than it is to learn the much harder rule. If the input looks like this pattern I know inside and out, I have to fight my core instinct to predict the next token.
You got it. It turns safety from a really hard suppression task into a much easier anomaly detection task. And neural nets are fantastic at anomaly detection when the distributions are distinct.
That has huge implications. It suggests we don't have to poison our models with bad data just to teach them how to refuse it.
We can potentially keep the weights completely clean.
I want to go back to the engineering side for a second because there's this section on weak to strong generalization that I think is so important for anyone who doesn't have a giant compute budget.
Oh, this was a great experiment. They basically asked, do I need a GPT-4 level classifier to filter data for a GPT-4 level model?
Because if the answer is yes, then it's turtles all the way down. You could never get started.
Right. So what they did was they trained a little probe on a tiny 13 million parameter model, a toy model, really, and they used that to generate noisy labels for a much stronger 224 million parameter model.
What happened?
The strong model improved on the weak labels. That is weak to strong generalization in a nutshell. Even though the labels from the little 13M model were noisy and imperfect, the bigger model was still able to robustly learn the distinction.
And I also tested this by just artificially making the labels noisy, right? Like flipping them.
They did. And they found that as long as you're aggressive enough with your filtering, so you prioritize high recall, even if it means low precision, you can filter out, say, 50% of your tokens, and the large model will still learn the retained stuff, the biology, just fine while forgetting the target.
So you don't need a scalpel. You can start with a machete as long as you have enough data left over for the model to learn from.
To a certain extent, yeah. It means you can bootstrap this whole process. You can start with a small, imperfect model to build your filter, and the big model you train with it will end up cleaner and more robust than the tool you use to build it.
Which basically democratizes this whole technique. You don't need access to Google scale compute to build that initial filter.
Exactly.
So to pull this all together, token filtering is more efficient, it scales better with model size, it creates this economic firewall against attacks, and counterintuitively, it actually makes refusal training easier through ode detection.
It really just checks all the boxes that post-hoc methods like unlearning have struggled with for years.
What do you see as the broader applications here? We've been talking about safety, but my brain immediately goes to things like copyright and PII.
Oh, absolutely. That is the sleeping giant application of this, for sure.
Because right now, if a model spits out personal information or copyrighted text, the company line is, well, we tried to filter our data set, but, some stuff slipped through.
Or they say, we used RLHF to train it not to say that. But the data's still in the weights. Legally, technically, it's in there. With token-level filtering, especially that removal method, you can make a much stronger claim.
You can say, we masked the gradients on these tokens. The model physically never learned this sequence.
It changes the entire legal conversation from we tried to hide it to it was never there.
And for copyright, you can solve the problem of training on, say, novels to learn linguistic style without memorizing the plot.
You could filter out the specific names of characters or key plot points at the token level while keeping all the rich vocabulary and sentence structure.
Surgical removal. I feel like that's the phrase that's going to stick from this paper.
I think so. And it solves that adjacent field problem. The fear that if you remove hacking code, the model will suddenly get bad at Python. This shows that if you're surgical at the token level, that collateral damage can be minimal.
Okay, before we wrap, I want to hit on that final idea they floated in the discussion about unsupervised capability segmentation.
Right. This is the really forward-looking, almost sci-fi part of the paper.
So right now, we are defining medicine and biology. We're building an external classifier to find those human-defined categories. But what if the model could learn to organize itself during pre-training?
The idea is, could the model self-segment? Could it learn just from its own internal representations to say, oh, this whole cluster of tokens and concepts relates to hazardous chemical synthesis, and then automatically just route the gradients for that stuff into a dead end?
So the model would basically develop its own conceptual immune system.
Exactly. Instead of us imposing these fuzzy human categories like hate speech, the model itself would segregate capabilities based on how mathematically distinct their features are. And given those weak to strong results we talked about, it seems like the model really does understand these features in a robust way.
If the features are there and they're distinct enough for a classifier to see them, then the model can see them too. We just need to give it the right architecture and incentives to act on that separation.
That's the next frontier, moving from us filtering the data to the model segmenting its own knowledge.
Shaping capabilities with token-level data filtering. It is a technical paper, it's dense, but I really think we're going to look back on this as a major pivot point, a shift away from the post-hoc RLHF era and back towards a more data-centric approach to AI.
I completely agree. It really validates that old saying, garbage in on garbage out, but it refines it. It's more like no poison in, no poison out.
We will have the link to the paper and the code repository in the description for you. If you are out there training models, seriously, take a look at that bidirectional classifier architecture. It is worth stealing.
Definitely is.
Thanks for tuning in to this episode of AI Paper Podcasts. Keep your gradients clean, and we'll catch you in the next one.